attending this special online defense. I'm assuming you are already familiar with Zoom and get used to the online presentation. So to like mentioned by Pratap, to better organize this presentation, if committee members have questions, please unmute and ask directly. If audience have questions, you can type it in the chat box. And I will pause for a while after each subsection, and I can answer your question. And you can also ask questions at that time. So before I start, I would like to thank my advisor and other committee members for their help and support during my PhD study and for my future career. So under their guidance, I made some contributions in the area of multi-robot coordination, which I'm going to talk about today. At the end of my presentation, I hope everyone knows why we need parsimonious communication, risk awareness, and resiliency when we deploy robots in real-world environments. So today, robots are already helping humans to automate some dull and tedious tasks, such as the robot arms collaborating with each other in the car manufacturing, and the warehouse robots are picking and packaging orders. As you can see from these videos, these robots are operating in the controlled environment. They are restricted to move to specific locations. So even though multiple robots are collaborating with each other, but they are under very constrained settings. So what I'm interested in is that robots are performing in natural unstructured environments. For example, the UAVs are flying in the air for the crop monitoring and fertilization, and the ground vehicles are delivering food outside. Also, the video at the bottom shows the robot swarm are performing reconnaissance in an interactive urban raid scenario. So not surprisingly, in this natural and unstructured environment, we need to deal with more difficulties and challenges. So for example, we need to worry about robot perception and the uncertainty from the environment. The noisy perception and the uncertain environmental conditions can usually put robot performance at risk and cause some safety issues. Also, compared with this controlled environment where all robots can communicate with the central server, in the unstructured environments, the communication quality cannot be always guaranteed. So there are many other challenges, such as the privacy issues that robots may share sensitive information. So among these challenges, I will focus on safety, uncertainty, and the communication. So for example, there are many safety issues, such as the inter-robot collision and failures. The left figure shows the accident of the self-driving car in Arizona. Also, if robots are performing in the adversarial environments, such as for military surveillance and reconnaissance, they may get attacked. And the attacks from these counter-UAV systems can block and compromise the sensors, such as cameras on the UAVs, or just make them fail completely. The safety issue can also be caused by the noisy perception. So for example, the sensors on the robots are typically noisy and have a limited sensing range, so which makes it hard for the robots to avoid nearby obstacles when the robots are moving very fast. So the limited sensing range also means in general, a robot may have local information and can only plan over a short time horizon. So sometimes you can see the situation can be even worse. The perception can be misleading. For example, the figure on the right shows the GPS signal on the drone is spoofed so that this drone flies off its desired path. So in addition to signal spoofing, the communication can also be spoofed or jammed. So the left figure shows that the jamming attack on the smart parking. The attacker is jamming the communication between the sensors deployed in the parking spot with this roadside unit, so that this roadside unit is not able to schedule parking for these vehicles. And when the robots are performing in the field environment, the communication is not always stable and reliable because of the limited communication bandwidth, communication delay, and noise. Sometimes communication can be a significant source of energy consumption, especially when the robot team has many small robots. The robots need to communicate over long distances. So to overcome these challenges, my research mainly contributes in 3 areas. Instead of individual robot planning, I focus more on the team-level coordination and planning strategies. that give hard guarantees with formal proofs. In particular, I design resilient and risk-aware coordination strategy to make robot team resilient to the worst-case attacks and be aware of the loss from the uncertainty. Also, to reduce the communication cost, I design parsimonious communication strategies that allow robots to be selective in when to communicate and who to communicate with. So I will give a brief summary of the work I presented in my proposal exam, which is marked in black. And today I'm going to focus on the research I have done after my proposal exam, which is marked in blue. I also did some joint work with my lab mates, marked in green. So most of the joint work are extensions of my current research. So I didn't include them in my dissertation because it is not my main contribution. I will give a brief introduction of them. So any questions so far? Any questions about the introduction and the contribution outline? Okay, good. So most of my research are motivated by the scenarios where robots are collaborating with each other to collect data in the environment. So for example, the drones can coordinate with each other to maximally cover the wildfire in the forest. Similarly, the underwater vehicles can jointly search the ocean floor. Also, as shown in the video on the right, the UAVs use down-facing cameras to track the targets, such as animals on the ground. So among these applications, I mainly focus on the target tracking case. So we consider a multi-robot target tracking scenario where each robot has a tracking sensor, for example, a down-facing camera. And the camera can identify a number of the targets on the ground. So here we use the colorful dots to show the footpoints of targets on the ground. So we assume that each robot has a set of candidate trajectories from which it can choose one to follow to cover some targets. So this is the natural constraint. And as we can see from this figure, robot 1 has 3 candidate trajectories. It chooses trajectories x11 to cover targets T2, T3. And the robot 2 has 4 candidate trajectories. It chooses trajectories x22 to cover targets T1, T2, T3, T4. And these 2 trajectories jointly cover 4 targets, T1, T2, T3, T4. We also notice that these 2 trajectories have the coverage overlap. So because of this overlap, the objective function, which is the number of the targets covered by robot trajectories, turns out to be a submodular function. So submodular function is defined on the set, such as a set of robot trajectories, and its main property is the diminishing returns property. So for example, adding a new element into a smaller set contributes more to the function value than adding this element into a larger superset B of A. So here the marginal gain means the new contribution to the function value. So to make it clear, let's see an example to show the submodularity in the robot coverage problem. So similar to the target tracking case, here each robot has a camera that covers a certain area. Now we are going to deploy a new robot. Let's see what is the submodularity in this case. So deploying a new robot R prime covers more new area after a smaller set of robots R1, R2 are deployed. Then after a larger superset of robots R1, R2, R3 are deployed. So this is because the area covered by the new robot R prime has less overlap with the area covered by the smaller set of robots. So which captures the diminishing returns property of the submodular function, adding a new element to a smaller set contributes more to the function value. So any questions about the submodular function? Okay, so given a function is submodular, the submodular maximization is to select a set S that can maximize this function value f of S. For example, we would like to select a set of robot trajectories to maximize the number of targets covered. So here, X denotes the matrix constraint on the decision set S. In our example, each robot can only select one trajectory from its candidate trajectory set, so which is the partition matrix constant. So this submodular maximization problem has many applications, such as the sensor placement, where we would like to place a set of sensors to maximally cover the environment. And also in the environmental exploration and the information gathering, the robots are jointly maximizing the information collected. Unfortunately, this submodular maximization is generally NP hard, so which means there is no polynomial time algorithm that gives the optimal solution. Or this kind of algorithm hasn't been found. So the good news is that there's a well-known greedy algorithm that runs in polynomial time, and it can give a suboptimal solution.
I have a couple of questions quickly. So
okay.
when you're trying to maximize coverage, right?
Yes.
Yeah, and there are problems that looked at maximizing coverage using, like, I can remember, for example, packing problems where you can avoid overlap and still maximize the coverage. They have been done in 2D and 3D. So why move towards the submodular where you allow overlap, but actually you don't want overlap anyways, right? So why not use packing problems or set covering problems, which have some tractable solutions at least?
Yeah, I think for this problem, the greedy algorithm is very efficient, and it can avoid the coverage overlap. Yeah, I mean, it tries to avoid the coverage overlap. Even for the set covering problem, I think if we want to solve it optimally, we can use the linear programming, I think. But it's not runs in polynomial time.
So is your area circular, or it doesn't? It's a random shape.
It can be a fixed shape. Yeah, it can be a fixed shape or a random.
Yeah, the reason I ask is because there's a bunch of tools that are actually. So the greedy algorithm, is it optimal?
The greedy algorithm is not optimal. Yeah.
Yes, that's why I'm asking. So there are some solutions that are not. I mean, they're not NP complete that have been used. For example, when we look at wireless networks in cellular systems, we use Voronoi tessellation, for example, to divide an area. We use some sort of packing problems to deploy base stations. And there has been some rather efficient solutions there that are better than the greedy of submodular, at least as far as I know. So have you explored those, or at least compared, or at least argued on why you specifically chose this one?
Yeah.
Compared to those, right? So I understand that the greedy is the best to solve this particular submodular formulation, but there are better formulations, right? So that's where my question is.
Yeah, I saw a bunch of papers that are using the Voronoi segmentation to solve this problem. But in that paper, the objective is also to coverage the environment, but it's more like a control problem. Yeah, but here we want to design the algorithm to place a fixed number of the sensors to maximally cover the environment. The reason is that you can see the greedy algorithm is very efficient. Yeah.
Yeah, but they're not, I mean, to be honest, they're not really for just for control, because we've used them, at least in the wireless community, not necessarily myself also, we've used them to, for example, deploy base stations at certain locations, deploy drones at certain for wireless coverage, to characterize cell association in a wireless system. And there's a bunch of rich literature there that already shows a lot of effective solutions. Of course, they've compared to these type of sensor placement, but because we need those, I mean, those type of algorithms are important in network planning. So I was wondering whether you kind of compared.
Okay, so I will look at that papers.
Sure.
I mean, if I can jump in, I mean, the main difference is that these are cardinality constrained sphere packing problems. Even in the coverage case, the main difference is that you have, 3 sensors, and the question is, what is the best place to put them? Rather than this is the space, what's the best coverage you can get in a sphere packing way. So it's really the cardinality constraint that it makes this different. Yeah.
Okay, sure.
Yeah, so in our case, there is a partition matrix constraint that you can see that each robot can only select one trajectory from its candidate trajectory set. But the total number of the trajectory you can select is bounded by the number of robots is also a partition matrix constraint, I think. Yeah. So.
I'm okay, you can continue.
Okay, yeah, so thank you. So the algorithm is, the greedy algorithm is pretty simple. So it incrementally picks the element with the maximum marginal gain to maximize the function. So for example, in the target tracking case, the greedy algorithm chooses the trajectory with the maximum number of the new targets covered at each round. So generally, the greedy algorithm can give 1 or 2 approximation of the optimal. So which means if the optimal trajectory covers 20 targets, the greedy algorithm can cover at least 10 targets. And more precisely, by using the curvature of the submodular function, the approximation ratio can be tighter. It is 1 over 1 plus kf. So the curvature measures how far the submodular function is from modularity or the linearity. So if the curvature is 0, then the ratio is 1, which means the greedy gives the optimal solution. So when the curvature is 1, this ratio is 1 over 2. So overall, we can see that greedy can give at least half approximation of the optimal. And it is the best known polynomial time algorithm for solving this problem. However, the greedy algorithm may not do well in some cases. So for example, there exists an adversary in the environment, and this adversary can attack some robots to block or compromise their tracking sensors. Or
can I jump in quickly? I just want to check one thing that you said on the previous slide.
Okay. Yeah.
Because I was turning my gears for a moment and it sounded a bit off. You made this statement that this 1/2 bound is very well known, right? And as you demonstrate, it's quite old. But you made this statement that so if the optimal solution can cover 10 targets, then the greedy would cover at worst 5. That's not exactly right, right? Doesn't your statement sort of strongly depend on F? It's not a direct analogy like that, right? I mean, it's going to get half of the optimal value. That doesn't necessarily correlate to covering 5 targets versus 10, does it?
So because
it's like half of the coverage value, correct? Or am I missing something here?
Yeah, because like the objective in this case is the number of the targets covered. So because the objective is a submodular function. Yeah, so this is why if the optimal strategy, optimal trajectory set, can cover 20, and our greedy algorithm can cover at least 10. Yeah.
So let me ask it a different way. Can I get, can I hit this lower bounds? So it's impossible for me to hit this lower bound with, while covering, say, more or less than 5. Do you see my point? I guess it's slightly confusing because F is not, I mean, it's certainly a function of the number of targets that you cover, but it's a coverage objective function, right? It's so I guess I don't see the one-to-oneness that's happening here. Maybe I'm missing something.
I think the F here is the number of targets covered. So it is.
Oh, it is. So that's the information I was looking for. Okay. Because there's a number of Fs that you could choose. And I guess my question was more, what is the F you're choosing here? I understand the F has to be submodular, but okay, good. Yeah, gotcha.
So we can see that overall, the greedy algorithm can guarantee at least half approximation, and it is the best known polynomial time algorithm for solving this problem. But if there exists some adversary in the environment, the greedy algorithm may not do well. So let's see an example. Yeah. So the greedy algorithm can do arbitrarily bad in this case if there exists an adversary in the environment. So for example, we would like to deploy 3 robots to maximally cover the targets. So here the targets are modeled by an importance map. And we assume that the targets in the dark blue region are more important than the targets in the lighter blue region. Now let's see how greedy algorithm deploy robots in this case. So the greedy algorithm will incrementally deploy a robot to a location which has the maximum new coverage. So in this way, it can avoid the coverage overlap to increase the joint coverage performance. So you can see that the greedy algorithm does very well in this case. However, when the robot that covers the most important area is attacked, the team coverage performance decreases sharply, right? Which means the greedy algorithm is vulnerable to the attacks. So instead, we may consider a resilient strategy to deploy robots so that they have some coverage overlap over the most important region. So in this case, even though some robot is attacked, the coverage performance, the team coverage performance is not changed that much. So here we can see we actually need some redundancy for countering the attacks. So this gives our first contribution. We design resilient coordination algorithms to counter worst case attacks. And this is a joint work with Dr. Papas at Penn. And more formally, we consider a max-min optimization problem where an adversary attacks alpha robots in the team of n robots. So this is motivated by the scenario where the number of the UAVs can be much larger than the number of the counter UAV systems. And we assume only some UAVs in the team are attacked. Because if all the UAVs in the team are attacked, we can basically do nothing. So even though we have this assumption, this problem is still very challenging because the robot team knows the attack number is alpha, but it doesn't know which alpha robots will be attacked. So considering this challenge, the robot team wants to maximize the number of the targets covered by selecting a trajectory set S. Remember that each robot selects one trajectory. While the adversary wants to minimize the number of the targets covered by removing a subset of trajectories A from S. So we can see it's like a game between the robot team and the adversary. So any questions about this problem formulation? Okay. So
just a very quick one. You're assuming there's a constant number of trajectories, right, for both? I mean, finite.
Yeah, of course. There's a fixed number of trajectories for each robot. Yeah.
Okay.
The finite set. Yeah. So there's some related work to guarantee resiliency for multi-robot systems. These papers mainly focus on the resilient formations of multi-robot systems, such as the consensus and flocking, where we want to optimize a submodular function that is defined on the entire robot team, such as the joint area covered or the total number of targets covered. Also, they consider the adversary as some malicious or misbehaving team member. This team member can manipulate the robot team to prevent it from achieving some goals, such as desired formations. So while we consider the adversary as an outsider, and it performs a denial of service attack. So for example, it can block the tracking cameras to make the robot lose tracking ability. And I will talk about this attack model again in the future work section. And for our attack resilient problem, we designed a centralized resilient algorithm because we're assuming that in this case, all robots can communicate with each other. And it gives a constant factor approximation of the optimal, and it runs very fast. It runs as fast as the greedy algorithm. And our algorithm contains two steps. So in the first step, the robot team makes oblivious decisions to pick out alpha most valuable trajectories. So the valuable means the trajectory covers the largest number of targets. So these alpha valuable trajectories can act as base to the adversary. So in this step, we don't consider reducing the coverage redundancy or coverage overlap because we actually need some redundancy to counter attacks. However, we don't want too much redundancy because if there is too much redundancy on the robot trajectories, even though there are no attacks, the team coverage performance can be very bad because all the trajectories overlap with each other. So for the remaining n-alpha robots, we use greedy algorithm for choosing trajectories. We know that the greedy algorithm can intentionally reduce the coverage overlap. So as you can see, our centralized resilient algorithm is the combination of the oblivious decision and the greedy decision. So any questions about this algorithm? Okay. And we show the centralized resilient algorithm gives the constant factor approximation of the optimal. And the approximation performance depends on the curvature of the function kf, and the number of the attacks alpha, and the number of robots in the team. And in particular, if the curvature equals to 0, the function is a modular function, which means only two trajectories cover totally different set of targets. So in this case, we can see that the approximation ratio becomes 1, which means our resilient algorithm gives the optimal solution. And if there is no attack alpha equal to 0, the ratio is 1/1 plus kf. So which is the same as the greedy algorithm. So because in this case, if there is no attack, we don't need to consider the first step to select alpha base. So all we need to do is the second step, the greedy algorithm. So this is why it has the same approximation performance as that of the greedy algorithm. And to verify the performance of the centralized resilient algorithm, we compare it with 3 other algorithms. And the first one is the optimal solution, so which is obtained by the brute force search. And the other 2 are the greedy and the random algorithms. So we can see that our resilient algorithm performs very close to the optimal solution. But the optimal solution is obtained by the brute force search or the exhaustive search. So it is very computationally expensive and only applicable to a few robots, where our resilient algorithm runs very fast, runs in polynomial time. And we can also see that our resilient algorithm covers more targets than both greedy and random algorithms, because in both greedy and random algorithms, these strategies don't consider the adversarial attacks. So any questions about the centralized resilient algorithm?
Yeah, I have a quick question.
Okay.
Do you assume, to solve this, do you assume that you know what the attacker is gonna do? So what is the action set of the attacker and what trajectories he can attack?
We don't know that. We only assume that the total number of the attacks is alpha, but we don't know which trajectory will be attacked. So this is why we formulate as the minimization problem. We want to optimize the worst case.
Yeah, so basically you know how many he can, I mean their capability, the worst case capability.
Yeah, we know how many robots, how many trajectories will be attacked, but which trajectory will be attacked, we don't know. Yeah.
Okay.
Yeah, but I have some follow-up work to deal with the unknown number of the attacks. We can talk about it later. Yeah.
Okay.
So in the centralized communication setting, all robots can communicate with each other to make decisions. What if the robot have a limited communication range and can only communicate locally? So we consider a distributed target tracking scenario where robots have limited communication range and each robot can only communicate with its nearby neighbors. So here the green line denotes the communication link between robots. So still we consider there is an adversary that can attack some robots to either block or compromise their tracking sensors. So in this case, the problem becomes even more challenging because we need to deal with both limited communication range and the adversarial attacks. Since we model the multi-robot target tracking as the submodular maximization problem, and we consider the distributed communication manner, so the related work can be the distributed submodular maximization. And there are 2 branches, research branches for solving submodular maximization in a distributed way. So the first one is the sequential decision-making strategy, where robots make decisions one by one to maximize the common submodular function. So for example, each robot makes a decision based on the decision from its previous neighbors. So here the arrow line denotes the information flow. And the second strategy belongs to the class of the divided and conquer method. And the problem in this paper is to select a small representative set from massive data. So the authors first partition the massive data into many small parts, and then select a portion of the representative set from each small part in parallel. So these papers give the approximation algorithms for a distributed submodular maximization, but they don't consider adversarial attacks. So building on this divided and conquer idea, we designed a distributed resilient algorithm. So it also has 2 steps. In the first step, robots form cliques based on the limited communication range. So you can see the clique is a subgroup of robots where all robots can communicate with each other. So this figure shows that these 5 robots form 2 cliques, and within each clique, all robots are fully connected. They can talk with each other. Then in the second step, all cliques perform the centralized resilient algorithm in parallel to counter the attacks. Because within each clique, all robots can talk with each other, so they can use the centralized resilient algorithm. So like I mentioned, this follows the divided and conquer idea. We partition the robot team into separate groups and run the centralized resilient in each group. So this is a new research I have done after my proposal exam. So before I introduce the distributed resilient algorithm, I would like to talk about some settings and assumptions. So first, we assume that robots can communicate and share information if they are within the limited communication range. For example, they can share their positions, they can share the set of targets covered. So however, each robot doesn't need to know the communication graph and how many robots in the environment. And the communication graph doesn't have to be connected because anyway, we need to partition the communication graph into separate cliques. And you can see later that our distributed resilient algorithm doesn't need too much communication among neighboring robots. And we have another assumption on the number of the attacks in each clique. We know the number of the attacks alpha is for the entire robot team, but how these alpha attacks are distributed among these cliques is unknown. So to deal with it, we take a conservative strategy. We assume that each clique also encounters alpha attacks. So even though it is conservative, we choose that it doesn't affect the final solution. Also, like I mentioned earlier, I have done some follow-up work to deal with the unknown number of the attacks. If you are interested, I'm happy to talk about it after my presentation. Yeah. So any questions about these settings and about distributed resilient algorithm? Okay. So let me talk about these two steps of the distributed resilient algorithm. So the first step is to form separate cliques among robots. This problem is called non-overlapping clique cover in the literature. So the objective is to partition the communication graph into fewer and larger cliques. So the problem is hard to approximate even for the centralized setting. So here consider the distributed communication manner. We design a distributed clique cover algorithm. So first I need to emphasize that it's just a feasible solution without the optimality guarantee. But it runs very fast. It runs in polynomial type. And this algorithm only needs 3 rounds of communication among neighboring robots. So in the first 2 communication rounds, each robot finds its clique. In particular, in the first round, each robot constructs its neighbor set. So for example, robot 1 finds its 3 neighbors, 2, 3, 4, and it constructs its neighbor set as 1, 2, 3, 4. So here we assume that the neighbor set includes the robot itself. So in the same way, its 3 neighbors, robot 2, 3, 4 can construct their neighbor set. And in the second round, communication round, each robot shares its neighbor set with its neighbors. Then after receiving the neighbor sets from neighbors, each robot finds its clique by intersecting its neighbor set with the neighbor sets from its neighbors. So let's see an example. So for example, robot 1 intersects its neighbor set with the neighbor set from each of its neighbors and store the largest intersection. So in this case, the largest intersection happens when robot 1 intersects its neighbor set with the neighbor set from robot 2 or from robot 3. And you can see the largest intersection is 1, 2, 3. So then robot 1 sets its clique as this largest intersection, 1, 2, 3. So in the same way, other robots can find their cliques. Any question about this clique finding? I'm sorry that there are a lot of neighbors and neighbor sets. Yeah. Okay, so but here the problem is that these formed cliques may have overlapping. So for example, the robot 1 finds its clique 1, 2, 3. Robot 3 finds its clique 3, 5, 6, 7. And these 2 cliques share robot 3. But remember, our goal is to form separate cliques. Then how to do that? So there's the very simple strategy. Robot 3 just join the larger clique, form clique 3, 5, 6, 7. 6, 7, because our objective is to form larger and fewer cliques. And at the same time, robot 3 will tells its decision to its neighbors. So this is the third communication round. And after 3 rounds of communication, these 7 robots form 3 separate cliques. And within each clique, the robots can talk with each other and can use the centralized resilient algorithm to counter attacks. Because you can see within each clique, these robots are fully connected. And all cliques can perform in parallel. So remember, in the centralized resilient algorithm, alpha robots make oblivious decisions, and the remaining robots make greedy decisions. So the alpha is the number of the attacks for the entire robot team. So I also mentioned earlier that each clique takes a conservative guessing and assumes it will encounter alpha attacks. So in particular, if the number of robots in this clique is less than alpha, then all robots in the clique perform the oblivious decisions. They just select the trajectories as base. Well, if the number of robots in this clique is larger than the alpha, the number of the attacks, this clique just follows the standard centralized resilient algorithm. That is, the first alpha robots perform the oblivious decisions, and the remaining robots perform greedy decisions. And all these cliques can perform in parallel. So any questions about these 2 steps of distributed resilient algorithm? Okay, so by this clique partition and the parallel resilient algorithm, we show that our distributed resilient algorithm has the constant factor approximation of the optimal. So similar to the centralized resilient algorithm, the performance depends on the curvature of the submodular function, the number of the attacks alpha, and the number of robots in the team. So because here we need to consider the limited communication and the distributed communication, so its performance also depends on the property of the communication graph. For example, the number of the cliques K and the number of robots in the largest clique. So in summary, its performance depends on the property of the function itself and the communication graph. And we implement this distributed resilient algorithm in Gazebo environment by using the multi-robot target tracking scenario. So in this environment, 10 aerial robots are tasked to track 50 ground targets. So each robot has 4 candidate trajectories: forward, backward, left, and right. And at each round, it will choose one to follow to cover some targets on the ground. So we assume that the noisy GPS position of the targets are known to the robots, and the robots use the Kalman filter to estimate the position of targets. And you can also see from the video on the right, if robots belongs to the same clique, we assign the same color to them. So here, 4 robots are attacked at each round. So if the robot is attacked, you can see its camera will be blocked and it will lose the tracking ability. So we assume that if the robot's camera is blocked at the current round, it can recover at the next round. So it is just a temporary failure. So we use this model only for the simulation. I will talk about planning our longer time horizon. And to verify the performance of the distributed resilient algorithm, we compare it with the baseline centralized resilient algorithm and the centralized greedy algorithm. So in both centralized resilient and centralized greedy, our robots can talk with each other to make decisions. So from the number of targets covered, we can see our distributed resilient performs very close to the centralized resilient. The baseline algorithm, centralized resilient, and covers more targets than the centralized greedy. So even though in the centralized greedy, our robots can talk with each other. The centralized greedy doesn't consider the adversarial attacks. So any questions about the distributed resilient algorithm? Okay, so in the target tracking scenario, robots are under temporary sensor attacks, and they are doing myopic planning at every time step. So along with one of my lab mates, I have done some work on longer time planning. So here, each robot actively plan its path with a limited budget in a finite horizon. So this problem is called Orienteering problem in the literature. So it is NB hard even for a single robot planning. So well, we want to plan paths for multiple robots to collect data in the environment. So still, we consider there are some robots will fail or get attacked. So building on my previous resilient strategy, we designed a resilient multiple path planning algorithm that gives the constant factor approximation of the optimal. So here you can see eta is the approximation ratio for the single robot planning problem. And we also show that our resilient path planning algorithm collects more data than both greedy and random algorithms. So this is a collaboration work with my lab mate. I didn't include it in my dissertation since it's not my main contribution, but this work shows that our resilient algorithm can be used for other applications. So in both target tracking and these team orienteering problems, we design strategies before the adversarial attacks. So we also studied how robots should react after attacks or failures. So we consider a team of robots jointly cover an environment. And our question is, if a robot fails, how many neighboring robots should be assigned to have compensated for the coverage loss? And our results shows that if more robots are assigned, for example, the robots within a larger help range are assigned, the remaining robot team can compensate for more coverage loss and has a larger coverage value. Well, at the same time, it takes more running time to replace the remaining robots. So basically, it's a trade-off between the, it captures the trade-off between the coverage performance and the computational effort. So again, this is a collaboration work with Dr. Sukami's group at USC. I'm not the main contributor, and this work is not included in my dissertation. So before I go to the next section on the risk awareness, any questions about the resilient coordination? Okay, so in practice, even though there are no attacks, the robot may still fail randomly due to some natural events, such as the antigen depletion, collision, or bad weather conditions. So the random failures give the uncertainty on the system performance. More broadly, the uncertainty can be from the unknown knowledge of the environment. So for example, vehicles have the travel time uncertainty because of the unknown traffic or the unpredictable traffic. So then the submodular function is not necessarily determinist, but can have some uncertainty. So specifically, we consider a stochastic submodular function, so which is still submodular in the decision set S, but now it is a random variable, and the randomness is induced by the new parameter Y. So Y can represent the uncertainty from the environment. And we know that the uncertainty can usually put the system performance at risk and cause some safety issues. So a standard measure for this stochastic submodular function is the expectation. So it measures the expectation measures the average performance, and therefore it is a risk neutral measure. Or we can consider the worst case scenario, like we did for the resilient target tracking case, which is very risk averse, but the decision can be conservative. So instead of the specific case, such as the expectation or the worst case, so it's better to have more flexibility to choose the risk tolerance. So we adopt a better risk measure from stock portfolio optimization, the conditional value at risk, also known as CVaR. So CVaR denotes the expected performance in the worst beta-tailed cases. So the beta is the user-defined risk level. You can see if beta is close to 0, then CVaR measures the worst case scenario. And if beta is 1, the CVaR measures the expectation of the entire distribution. Then CVaR is the expectation. So we can see the biggest advantage of CVaR is that it gives more flexibility for the user to choose the risk he or she would like to take by tuning this parameter beta. Well, for the expectation or the worst case, the user can only make decisions based on either average or the worst case. So we consider maximizing CVaR instead to make the risk-aware decision with more flexibility, which is our second contribution. So we design a risk-aware coordination strategy to managing the risk of performance loss. So more formally, we consider maximizing CVaR over the decision set S. So from this equation, we can see that the CVaR measures the expected performance in the worst beta-tailed cases. So here we consider a centralized decision-making problem to select the set S, the decision set S, by optimizing CVaR. And we use the sampling method as an oracle to compute the value of CVaR. And we also assume that the distribution of this Y represents uncertainty is independent of S. Any questions about this problem formulation?
I have a quick question. Usually for the CVaR, if you don't have the tails, it's not tractable to compute. So do you assume you have the tails, they can be quantified, or so how did you compute the CVaR?
Yeah, we use a sampling method, yeah. So yeah, we know the distribution of Y, and we give maybe 1,000 samples of this distribution and compute the average, yeah.
Okay, and the second question kind of related. So usually when you design your system to optimize the CVaR, that might actually make the average worse. Would that be a problem in your system, or you just care about the worst case, the average is okay? So there's usually a trade-off between the two, right?
Yeah, that's true, yeah. So we, so actually in our simulation, we varying this parameter beta, and when this beta is very small, we get the worst case scenario. When this beta is 1, we get the expectation. We actually compare these two, these two performance, and we can see the trade-off.
So that's a random field that you're approximating, right, over Y?
Yeah.
Yeah. So so whenever, I mean, you can just say that you're taking samples, but there's a right. You have to worry about the interplay between the variance error and the approximation space error. You can't just take 1,000 samples and hope that it's going to be correct. It may not. I mean, you have to choose an interplay between the dimension of your basis for approximating the function and also the number of samples.
Yeah, that's true. Yeah, we actually we use some results from the previous paper, and I mean for the same problem. They basically shows that if the number of samples is larger than some value, we can have a very small approximation error. Yeah, we use that result.
Well, we can talk about that later.
Yeah, okay.
I don't agree with that last statement you made, but we can talk about that later.
Okay, so the importance of this optimization problem is that it bridges the gap between the high-level ideas of the risk awareness and the low-level specific planning for the robots. So there's some related work for optimizing CVaR, and this paper is the seminal work. This paper is the seminal work for CVaR optimization on the continuous decision variable X. So by assuming this utility function follows the Gaussian distribution, the authors solve this problem by the convex optimization. And for the discrete decision variable, these two papers give some positive results for selecting a portfolio or a distribution over available C sets. And they give the constant factor approximation algorithms for optimizing CVaR. However, for selecting a single set, there's only some negative result. For example, this paper shows that the CVaR optimization problem is hard to approximate. So for solving this problem, we designed the first polynomial time algorithm for selecting a single set to optimizing CVaR. And in particular, we designed a sequential greedy algorithm, which builds on the standard greedy algorithm. And it gives the bounded approximation of the optimal and runs in polynomial time. So you can see its approximation performance contains two parts. And one is from the constant factor approximation. It's 1 over 1 plus kf, so which is from the standard greedy algorithm. And the other term, some approximation error. So this CVaR-based submodular optimization can be used in many robotics applications, such as robust environmental monitoring, where the robots have random failures. And by tuning this parameter beta, the user can be either risky or conservative to place robots for the environmental monitoring. It can also be used for multi-robot task assignments, where the robots have travel time uncertainty. So for example, we consider assigning multiple robots to serve multiple task locations. And for each task location, there can be multiple robots assigned to it. And we follow the first to come, first to serve principle. That is, only the robots arrive first at the task location can be chosen. So this setting may be conservative, but it can be used for emergency cases, such as the firefighting or medicine supply, where we want at least one robot comes to the emergency location as quickly as possible. So because of the unknown traffic, we assume that the robots have travel time uncertainty. So for this assignment problem, we can use our risk-aware sequential greedy algorithm to solve it offline. That is, we compute a risk-aware assignment at the initial time step and fix the assignment afterwards. However, the offline assignment doesn't take advantage of the real-time information, such as the locations of robots and the traffic condition. So we want online algorithms that can utilize this real-time information for better performance. So in the online setting, the assignment can be rescheduled to adapt to the real-time information, and then these task locations can be served earlier. For example, in this figure, at the initial time step, robots J and robot J and K are assigned to the blue task location, and robot L is assigned to the red task location. However, when the robot J arrives at the intersection, if this traffic light is green, it can go directly to the blue task location. So in this case, it's better to reassign the robot K to the red task location to reduce the waiting time there. So you can see that the online assignment can utilize this real-time information for better performance. So one naive online strategy is to schedule reassignment at every time step. Then the real-time information can be fully utilized. However, the bad thing is that it will take a lot of computational effort. So we design an online strategy that triggers the assignment only at a specific time steps instead of all time steps. So in this way, we can use the real-time information and at the same time, save some computational effort. So the main point is to decide when to trigger the assignment. And our idea is pretty straightforward. Consider robots assigned to the same task location. For example, the robots J and J prime are assigned to task I. And if the average travel time of robot J to task I is less than the average travel time of J prime to task I, and its travel time of robot J has less uncertainty. So in this case, we can see it's most likely that robot J will arrive at the task I earlier than robot J prime. So there's no need to continue assigning robot J prime to task I. Instead, we can trigger the assignment to assign robot J to the other task locations to reduce the waiting time there. So this triggering condition has two inequalities. One is the average travel time inequality, and the other is the uncertainty inequality. So in this equation, the gamma is the triggering ratio, which regulates the triggering frequency. So for example, if gamma is large, for example, say gamma is close to 1, then this average travel time inequality can be satisfied more frequently, and more assignments will be triggered. So any questions about this triggering condition? Okay, so to see its performance, we compare the online triggering assignments with 3 triggering ratios to the offline assignment and the all-step assignment. So from the waiting time at the task locations, we can see the triggering assignments performs very close to the all-step assignment and work much better than the offline assignment. While at the same time, the triggering assignments schedule fewer assignments and take less running time than that of all-step assignment. So we also notice that the triggering ratio gamma plays the trade-off between the performance captured by the waiting time and the computational effort captured by the number of assignments and the running time. So this online triggering assignment is the new research I have done after my proposal exam. And any questions so far? Okay, so the idea of the triggering condition can also be used to design parsimonious communication strategies because the robots can be triggered to communicate at specific time steps instead of communicating constantly to reduce the communication cost. So because I already present this part of research in my proposal exam, here I will briefly go over it. So we first design a when-to communicate strategy by using the self-trigger control. We evaluate in a multi-robot target tracking scenario. So here robots are moving on the convex boundary to track a target inside. So the objective of the robots is to form a uniform distribution around the target. And we design a self-triggered communication strategy where each robot communicates with its neighbors only at certain time steps, instead of communicating with them constantly to reduce the communication cost. So in this way, you can see more than 30% of communication messages are reduced with a similar convergence speed. So to further reduce the communication, we design a who to communicate with strategy in a multi-robot, multi-target assignment problem. And we assign the robot subsets to track the targets based on the observability measures. So the objective is to reduce the uncertainty in the target's position. So we design a greedy assignment algorithm that restricts the robots to communicate within the small groups instead of communicating with all the other robots. So in order to reduce the communication cost. So even though with the limited communication, we show that our assignment algorithm gives the constant factor approximation of the optimal tracking performance. So that's all about my current research. And in summary, we designed two parsimonious communication strategies to reduce the communication cost. These strategies allow robots to be selective in who to communicate with and when to communicate. And we design a risk-aware coordination strategy to managing the risk from uncertainty. It allows a user to manage the risk by tuning a risk parameter. And we verify the performance of the risk-aware coordination in both offline and online multi-robot task assignment scenarios. Also, to counter the attacks, we design both centralized and distributed resilient algorithms to guarantee team-level tracking performance. Any questions so far? Okay, so this current research also opens up some future research directions. And the first one is about communication attack. So in my dissertation, I mainly focus on the attacks on robots or their sensors. So for example, an attacker attacks the robots by blocking their tracking cameras to make them lose tracking ability. So the adversary can also attack the communication link among robots. So if this link is attacked, these two robots cannot communicate with each other to share information. So we will focus on how to counter this kind of attack. Some possible strategy can be adding some redundancy over the communication links or replace the robot after the attacks or failures. But first, we need to figure out how badly this type of attack can affect the team level performance. And we will also consider other attack models. For example, the adversary can be some team member. So I already talked about this attack model in some related work. For example, these key robots in the team can be non-cooperative, and they can spoof other team members by telling them the fake actions. So compared with the worst case attack from an outsider, this attack model is weaker, but it's harder to detect. So one idea is to form a game between the well-behaving robots and these misbehaving robots. Other future research directions can be the extension of my a risk-aware algorithm to the vehicle sorting problems, such as multi-robot TSP or team Orienteering problem. So if you are interested, we can talk about it later. Any questions about my future work? Okay, so, and here I list the work I have done during my PhD study. I include the upper section in my dissertation, and it contains the parsimonious communication, resilience, and the risk-aware coordination. And the lower section contains the joint work with my lab mates. I didn't include this part in my dissertation because I'm not the main contributor. And I have been working with people inside and outside of Virginia Tech. Thanks so much for their help and their contributions. So that's all about my presentation, and thank you, and feel free to ask any questions. Thank you.